Hey folks, welcome back. So we are going to finish up our work in section 7.2. We are trying to rule out the existence of limit cycles and closed orbits in general. And the final of the three criteria for us to check that will rule out these limit cycles has to do with a notion from vector calculus. So in order for us to really figure out what this new third criterion means, we have to double back a little bit and recall some basic facts from vector calc. Seeing how vector calc itself is not a prerequisite to the class, that's fine, because you should have also seen at least some of this material in at the end of multivariable calc. So that would be Green's theorem in particular. Right, this is kind of the first real generalization of the fundamental theorem of calculus. And what we need from there is the notion of divergence for a vector field. Right, we want to figure out how something is kind of spreading out over time. So let's see if we can't fill in any gaps that might be there. So recall what the divergence of a vector field is. So a vector field for right now, we are going to take to be a function from Rn to Rn. So every location in, say, the plane is going to be assigned a two-dimensional vector, right? And this is the whole reason why we're doing this in this particular fashion, is that vector fields from one dimension to the same dimension can actually be represented geometrically very nicely. We've already seen this. This is exactly how we're representing our vector fields in the plane. So everything we've been doing so far with phase planes has been kind of a representation of a vector field in R2. And what we're doing here is we're assigning a function to that vector field. We are saying for this vector field, we are going to compute the trace of its Jacobian matrix. Okay, so the divergence of a vector field is the trace of df. Now, to see this, I mean, it's not too hard to see exactly how this relates to our usual, what would this be? It would be differential notation. It's not too hard to see what the connection is here, right? In general, the divergence is something that's going to be invariant based on coordinates or based on choice of coordinates. And this is why I'm giving you this definition, that it's the trace of a Jacobian, because that trace is invariant of coordinate choice. Now, when we do this in Calc 3 or in vector calc, what we usually do is define the divergence in terms of this grad operator, or this del, which is the vector of all first partial derivatives with respect to a given coordinate system. So the divergence actually is coordinate dependent when you define it like this. Right? Divergence is going to change when you use Cartesian coordinates, whereas you use cylindrical coordinates, polar, spherical. Any curvilinear coordinate change is going to change the definition of the divergence, which is why I try to avoid giving it in this coordinate-dependent notation, and I go for this instead, being the trace of the divergence. And if you want to go even further, no, we'll go ahead and we'll stop. Yeah, that's all you need. Oh, also I was thinking of something else. Never mind. But yes, we'll go with the definition that I've given. But we do match this up and say that the divergence, we're used to seeing it as this sum of first partial derivatives. And we can match that up with the definition. Sure enough, this is the trace of the Jacobian matrix. But that will change, right? The del operator changes depending on your choice of coordinates. So it's much easier to use the coordinate independent version to make sure you're defining the correct thing, or you're capturing the correct notion, right? And if we want to move this into 3 dimensions, then sure, you see the same exact phenomenon. That, well, it's just going to be summing down the diagonal of the Jacobian matrix itself. Okay, so divergence in particular only applies in this setting where we go from one dimension to the same dimension, or in particular we go from one vector space to the same vector space. for that vector field. Okay, so now that we remember what the divergence looks like, also remember that we have the divergence theorem, or recall. It's a loaded word, recall. Sometimes people have taken the class, sometimes they haven't. So for right now, we can take this statement as fact. Now, what you should be thinking of for this theorem, yeah, it looks a little daunting. This is a flux integral on the left and a triple integral on the right. But what they are doing is they're giving us two different manifestations of the same phenomenon. That we're saying that the amount of stuff passing through the surface of an object, right, or the total amount of stuff passing through is exactly equal to how much that stuff spreads out from the inside, right? If we're adding something to the interior of the object, then it has to be seen on the boundary. Think like blowing up a balloon, or maybe like a wire mesh balloon. You are adding air into the balloon as you blow it up, but as you add air to the interior, that air has to either expand the balloon where no air is passing through the boundary, or if you have a mesh balloon where that air has to then flow through the mesh itself. And that's what we're saying here. On the left, it's what's passing through the boundary, and on the right is what is expanding from the center, or from the interior. And Gauss's theorem, the divergence theorem, says that these two quantities are the same. Okay? But in particular, we're going to use this to our advantage to define this notion of, define a physical notion of what the divergence is doing. So I'm saying it's measuring how stuff spreads out. Let's verify that. If I were to take an arbitrary object up here, an arbitrary region, omega, and then squeeze down its volume infinitesimally, right? I'm going to go ahead and take the limit as this volume gets really, really small. Then observe what happens on the right-hand side. That if I am working over a very small volume, then the divergence is really not going to change that much across the entire region. So what I can say is that I can evaluate the divergence at a specific location. Right? I have a specific value, a specific constant number that represents the divergence for the entire region. And then I'm saying, let's just go ahead and multiply that by, well, whatever is left over. And this will be the volume of the region. Okay? So if you want to think about that from a calc standpoint, from a single variable function standpoint, so think about it, a function y equals a function of x. So you could go ahead and take an integral over this region, sure, and that would be the integral, what, a to b of whatever the function is. No problem. But if I zoom in far enough, or I zoom in close enough, then this piece just becomes a very shallow portion, right, a very shallow region here over a very, very small delta x. So that would mean that I can effectively just take some representative value here for f. This will be f of some, I don't know, x star. Don't confuse that with a fixed point, but f of x star would effectively represent the volume. So this is effectively the area of a true rectangle if I zoom in close enough. And the same phenomenon is happening up here in the three-dimensional case. I can go ahead and compute the hypervolume, or just the volume in general, but I can compute the hypervolume contained by this function up here, this df, or divergence f, by saying because the volume is small enough, because the region is small enough, I can just go ahead and factor out some constant value that represents the divergence over the entire region. And what's remaining here, this is just the volume of the region. This is just the volume of omega. So that flux integral, due to the divergence theorem, the right-hand side, oh shoot, wrong thing. Right-hand side becomes this down here, right? It becomes the right-hand side of this approximation. And the left-hand side, I get the equality due to the divergence theorem. Oop. Okay, there we go. So, the tour moves on. All right, and once we have that approximation, we say that Divergence then, if I go ahead and take this volume piece and throw it underneath the flux integral, I divide through by the volume, and take the limit as that volume goes to 0, then I see an interpretation for what the divergence is, at least on an infinitesimal scale. That the divergence of a vector field is its volumetric flux density, right? So at each point, it's telling me how things want to flow, how the total amount of stuff that wants to flow. Is it flowing into to the infinitesimal region where I get a negative value, or is it flowing out where I get a positive value? Now, if that divergence is 0, we could have a net 0, so some bits coming in, some bits going out. So it's not necessarily that the divergence being 0 means that nothing is moving. No, it's just that there is no net movement through that region. And you'll see that with saddles in particular, right? So there's a net, let's see, if I zoom in close enough here, we will see that there's stuff coming out in this direction, but there's also stuff coming in this direction, and likewise, stuff going in, stuff coming out. The divergence at a saddle should be 0, or it should look really close to 0, or there are prototypes that make that 0. But I digress. The divergence is a flux density, and that's what we're using it for when we talk about Dulac's criterion. So, finally, to talk about Dulac's criterion, the proof is going to use Green's theorem. And Green's theorem is a more specific version of the divergence theorem. And that itself is a special case of the generalized Stokes theorem, which is, in turn, generalizing the fundamental theorem of calculus. So if you didn't have enough motivation to take vector calculus, now you have some. Right? This is actually a really, really great a deep insight into how things change, right? You're measuring you're measuring a total net change in something in 2 different ways, right? So let's see what this version looks like. So for Green's theorem says that we need to be doing this over a simply connected domain, right? Because we moved up from 1 dimension in the fundamental theorem of calculus, we have changed the topology of what's happening here. So we need to change our notion of what a closed bounded interval looks like. So usually we're just talking about the integral from a to b of f prime of x, and this is just f of b minus f of a, right? This is the fundamental theorem of calculus that we know and love. And then Green's theorem gives us another version of that. It moves it up a dimension. So instead of talking about a single integral on the left, so 1 integral on the left and no integrals on the right, now we have 1 integral on the left and 2 integrals on the right. Okay, so there's always this trade-off in dimension. We're saying that the effect on the boundary is influenced by integrating some function over the interior. Right? And this is exactly what we're doing with Green's theorem, divergence theorem, Stokes theorem. We are measuring a net change in 2 different ways. And a simply connected domain here just means that I can fill up the entire thing. It looks like I can contract this thing to a point. And this is different, right? If I put a hole in here, then this is not simply connected, right? Because I won't be able to contract this whole thing to a point, right? So simply connected means, in this case, contractible to a point. Okay, so when we are integrating over such a region, then the first and probably most common statement of this theorem is that there's a circulation around the boundary, right? The left integral here, this work integral on the left, says this is how much of f points in the same direction as we travel along the boundary curve partial d. And that this circulation, right, the total amount of work done in the same direction as the curve, is actually going to be given by how this vector field is circulating in the interior. Right, I won't go into details about why this is true, but this is circulation on the left, and circulation density on the right. Okay. Now, that brings us to the second statement, the one that we're actually going to use for Dulac's criterion. And this has to do with, hey, you guessed it, the divergence. Yep. So what we're doing here, I would like to call your attention to these two locations in the diagram. The first has to do with how much of F is pointing in the same direction as, we'll put the F in there, I suppose. This is how much of F points along the direction of travel, whereas on the right here, we're measuring how much of F points perpendicular, right? How much of that is outward pointing? So how much leaves the interior domain D? Okay. So statement number 2 is what we're looking for here. We're measuring how the vector field wants to spread out over a simply connected region. And then we're measuring that flux through the boundary by some divergence, some density of the interior. Okay, so in plain English, there you have it. The net circulation of F around the boundary is the double integral of the absolute value of the curl, and that is the circulation density. Circulation density. Okay, now, Dulac's criterion makes use of the second form, the divergent form, so that the net outward flux of the vector field through the boundary of the region is the double integral of the divergence, the flux density over the region D. Okay, which is exactly what boundary D contains, which is exactly why we can't have any holes in this region. We don't want to be skipping out on something interesting that might be happening inside a puncture. Okay, so in order to apply this to planar systems, right, Dulac's criterion is a planar phenomenon, right? This is why we're using Green's theorem and not some higher dimensional version of Stokes. But Dulac's theorem says for us to be in the setting for Green's theorem, that we have a vector field, little f, over a simply connected region D. And we are going to define the system x dot equals f of x. So our usual system, but we're doing this over a C1 vector field on a simply connected region of the plane. So if there exists some function, some modifying function, some scaling function, such that the divergence of the scaled vector field, g times f, is non-zero on D, right? It never changes sign, okay? So specifically, we need to make sure that grad or dot, whatever you want to call it, diverge, is strictly positive or strictly negative on D, right? This is the condition. Then there can be no closed orbits for the system sitting inside that domain D. And within that theorem, there is a definition for what this little g function is called, and some literature calls this a Dulac function. Okay, so let's see what this means exactly. So coming back to Green's theorem, remember, we're looking at the divergence form, so we're paying attention to the right-hand side of that theorem to say that the divergence is strictly positive or strictly negative. Okay, and then we're comparing that against a closed loop integral wherein something should zero out. So here's the proof. It's by contradiction. Suppose that there was a closed orbit for the system sitting entirely inside of D. Then it would have to bound some simply connected region D in the plane, right? Closed orbits are simple closed curves. The Jordan curve theorem says that there is a bounded region, a compact region that is contained within that curve. There's also another side, there's an outside to that curve that's unbounded, but we're going to focus on the bounded region. So Green's theorem, the divergence form of Green's theorem, would apply. And so we're going to go ahead and say that there's this function E. Remember, we're trying to say this is kind of like an energy. And in this case, since we're making this look kind of like a flux integral, or kind of like a work integral, that this should be some version of an energy or a work quantity. So I'll call it E for energy. And we're going to go ahead and call that the double integral of the divergence of GF. Now, GF, I can go ahead and pull the G I can go ahead and use Green's theorem to go ahead and say that this is the same thing as me just taking the outward, like the outward normal flux integral of G times F. So I'll even put little parentheses around that guy. Okay? So I can go ahead and exchange the double integral of the divergence for the closed work integral of the vector field GF. Now, GF, I can go ahead and pull the G out of that dot product and remind myself that F is just equal to X dot. So, if I were to go ahead and parameterize the curve, I can go ahead and notice that X dot here, I don't even have to parameterize it to know this, but X dot and the unit normal have to be orthogonal to one another. They are perpendicular. So that means that I'm integrating a zero function, which means that the work integral on the right has to vanish. So that means, that would mean that the E function that I defined, or the E value, actually has to be 0. But that can't be the case, because this GF function has a divergence by assumption that is non-zero. Okay, so there has to be a non-zero value for the integrand on the left-hand side. This whole thing would then go ahead and make E into either a positive or a negative number. Okay, but we've just shown that E actually has to be 0 if we have a closed orbit. So E is both 0 and one of either positive or negative, which can't happen. So the contradiction shows that there are no closed orbits in this system. Otherwise, we get this contradictory information. Okay? Therefore, there can be no closed orbits. Let's actually see this in action. So consider the following system. This system I actually pulled straight from the textbook, so feel free to go ahead and follow along with their exposition. But here's the deal. We can go ahead and ignore the scaling function, right? We can just go ahead and say G is equal to 1 for all intents and purposes, right? So up here, G is identically the 1 function. And notice that this function has a divergence, or the vector field has a divergence that comes out to this. You can check that on your own. I highly recommend that you do. And this function is positive only, right? We notice that there's a perfect square sitting in here, right? Negative x minus 1 squared. So the divergence is positive only when y is less than negative x minus 1 squared. And it's negative for exactly the opposite, the exact opposite inequality. So, let's see. This would mean that I could take two different candidate regions for what my D space looks like, or what the domain D looks like. And these regions I've gone ahead and outlined below, right? And these are separated by this parabola y equals minus x minus 1 squared. So I can definitively say, based on Dulac's criterion for the function little g equals 1, so right up here specifically, because I'm taking g equal to 1 as my Dulac function, that I can go ahead and rule out the existence of limit cycles to either side of this parabola. Right? My divergence is exactly 1 sine to either side of that curve. Hence, no limit cycles can exist in that region. But, have a look here. I can change up the g function, and this is the one that Strogatz uses. Right? Sometimes you have to be a little bit creative in how you come up with these guys. we can go ahead and say that the same system using a different Dulac function can change up those domains. So instead of ruling out limit cycles in these two regions, I can use a different function to change up what those regions look like. So the g function I can go ahead and write as this vector field here, so that would be right there. And this guy has a divergence that looks like -1 over y, right? It's actually shockingly simple given how complicated the functions look. But the divergence is just a -1 over y. And this gives us a completely different function to consider, right? And this will change up the domains where we can rule out the limit cycles. Okay? So let's have a look. So if I were to go ahead and use this Dulac function, the divergence of GF is positive if and only if, right? If and only if this -1 over y, divergence is positive, if and only if 1 over y is less than 0. And that would then split this guy into 4 different regions. Okay, so if y is less than 0, so if I'm sitting in the lower half plane, then I get a positive divergence. So I could rule out limit cycles in this entire half plane, but I do have to be careful because g itself was discontinuous across the coordinate axes, right? I can't let either x or y be 0 in this case. So that means that I have to split up my regions into the 4 coordinate quadrants. So there is a positive divergence down below, but I do have to be careful that I take into account the domain of the g function as well. So this vector field is not defined on the coordinate axes. And the same goes for the top half plane, the upper half plane, but this time I'll go ahead and get a negative divergence instead. So that means I could rule out limit cycles for all 4 of these regions. Right? That's not to say that these limit cycles can't cross into different regions, just that if I tried to close up an orbit here, then Dulac says I can't do that because I have a non-sign changing divergence in that region. Okay, so no closed orbits can exist within any of the 4 coordinate quadrants. So there are 4 regions because of the discontinuities in the g function that we need to consider. And this final argument here, the last 2 examples might lead you to believe that we can go ahead and choose a g function, a Dulac function, that would change up the domains where we can consider closed orbits, or we could try to actually change up the function so that there are no closed orbits anywhere in the system. And unfortunately, that's just not true. It's not realistic, and more importantly, it's just not true. Okay, so we can change up the g function. There's a lot of flexibility in here, and yeah, you can't teach creativity, so what I'm going to do is show you how I think about the problem. So let's consider this system as a prototype, right? You might recognize this as one of our systems in the Hopf bifurcations prototype, or the normal form. This is the positive trace, so this is the supercritical Hopf, or the supercritical side of a Hopf bifurcation. So anyway, we'll get to that later. But we have seen this, and this system has a counterclockwise unit circle, or has the counterclockwise unit circle as a limit cycle. Okay, so this system has a limit cycle, is the bottom line here. But any region containing D, or D that contains that limit cycle, and any function g that I'd like to take to be my Dulac function, would need to satisfy the following equation, right? The divergence of that vector field would have to hit 0 somewhere. Okay? That needs to happen, right? Otherwise, there is a region here that contains the limit cycle, and or hopefully it's a simply connected region, but there is a region here that would have to rule out the existence of the limit cycle that actually exists inside of the region. So I need to make sure that this divergence is 0 somewhere, or I know that it is. It has to be. So let's use that. In particular, let's see what happens when we are on the unit circle itself. And that would be enough to kill off this entire term on the right. So that means that grad g dot f has to be 0 somewhere on the unit circle. Okay? So first argument here, I should probably draw a quick picture. The idea is that there is a limit cycle in here. This is the unit circle. And for that unit circle, I am going to go ahead and try to contain it with some simply connected domain here, D. Okay? So that's all I'm saying, is that this divergence has to be 0 somewhere within this region D. And in particular, if I were to restrict this so this only occurs near the limit cycle, so if I restrict this guy down, let's make him nice and bold. If I were to, restrict so that I look in a neighborhood around here, technically I'm going to have to include some stuff in here, but my point remains that I'm going to have to make sure that somewhere on the unit circle, right, this piece dies off, which only leaves this side, or this term on the right-hand side of the divergence. And that would mean that grad g dot f has to be 0 somewhere on the unit circle. Okay? So I need to establish this. So if this guy wasn't 0 everywhere, or was non-zero everywhere, then there is a positive or negative function that represents this value right here. This would be the change in g as I traverse the limit cycle, right? So this function would have to be strictly positive, right? This change in g can only be increasing along the unit circle, and we run into the same issue that we did for Lyapunov functions, that this is not going to be the case if I have a continuous function. So this guy has to increase, but he also has to come back to where he started, and that makes a contradiction. Okay, so any Dulac function that I choose actually has to violate this, this condition across the unit circle. It has to violate this grad g dot f equals 0 somewhere along the unit circle. And that means that I cannot apply Dulac's criterion over any simply connected domain that includes the unit circle. So the conclusion here, this is a kind of an advanced argument, but there are no Dulac functions for this system over, and I should say, simply connected domains containing the unit circle. Because otherwise I wind up with this argument where I can say the Dulac function has to be discontinuous and continuous at the same time as I traverse the limit cycle itself. And that would kind of rule out this option that we can just kind of play fast and loose with what domains we want to use or what Dulac functions might exist. So it's interesting but advanced. I'm not going to test you on this necessarily, but it's an interesting argument to kind of wrap your head around. And that will do it for this section. That those are the 3 different ways for us, or 3 primary ways for us to rule out limit cycles in certain planar systems. You got to show that this guy is either a gradient system, that it has a Lyapunov function, or that it satisfies Dulac's theorem or Dulac's criteria, or criterion, I suppose. Okay, so that'll end section 7.1, and we're going to go ahead and jump on into 7.3, where we talk about the exact opposite. Instead of ruling out limit cycles, let's see when we can force them to exist.